Okay, I'm going to encourage you when you have to go find zeros of a polynomial, go put the polynomial into your calculator. So I did that. Into my y equals, I typed in the polynomial, and then I did a zoom 6, and I hit graph. There's my polynomial. It's degree 4, so even degree. Let's talk about end behavior. Even degree, the leading coefficient was positive. What should the end behavior be doing? Should be going up, up, does it? Yes. It's a degree 4, so what's the most number of turning points it could have? N minus 1, right? So 4 minus 1 is 3. It has 1, 2, and then down here is 3 turning points. Okay, it's a degree 4. What's the most number of x-intercepts it could have? 4, but how many does this one have? 3. Well, sort of. This one might be a multiplicity 2. Do you see why? It touches and then goes back up, right? Okay, there's the graph of it. So let me go kind of put in a picture over here. And it looks like maybe -1 and 3, possibly. Goes down, touches, way down here. Ugh. Something like that. You agree? Quick sketch. Okay, let's go list all the possible rational zeros. That's what we've done today, right? Possible rational zeros. P over Q. Where's P going to come from? -12. Where's Q going to come from? The 2. So up above, P is 12. So what's the list of P? 1, 2, 3, 4, 6, and 12. Q was 2, so I get 1 and 2. Could you give me the list of all possible rational zeros of that polynomial? Plus or minus? First, I'm going to put all the p's over 1. What do I get? 1, 2, 3, 4, 6, and 12. Now what happens if I put them all over 2? What list do I get? 1/2. Let me keep going and then I'll pause and fix everything. 1/2. 2 over 2 is 1. 3/2. 4 over 2 is 2. 6 over 2 is 3. And 12 over 2 is 6. So there's my list of all possible. Resuming after the power cut off. We've listed all of our possible rational zeros. And then since you have technology in your hand, you went and looked at the graph. And you were able to verify when you hit trace -1, enter. Trace -1, enter. You were able to verify, no, should be -2. Where did I get -1? I have no clue. So on my graph, let's do it this way. -2, like that. That should look better. Okay, I said -2, enter, and I got a 0. And then I did 3, enter, and I'm going to get a 0. So I know -2 and 3 are indeed zeros, only because I have technology in my hand. But I'm going to go do both of those zeros over on my little synthetic division. So let's go put 3 in the little half box and see what happens. What are my numbers? 2, 3, negative 15, negative 32, and negative 12. So I'm using positive 3, which is in my list of possible rational zeros. I am now by hand verifying that 3 is indeed a 0. You can verify it by looking at your calculator. I'm old, I don't have a calculator. I want to verify by hand that yes, 3 is a 0. Drop it. 2 times 3 is 6. 9 times 3 is 27. 12 times 3 is 36. 4 times 3 is 12. Did I just verify that x equals 3 is a 0? Yes. Because my remainder was 0. What other number could I show is a 0? Let's do negative 2. So negative 2. I'm just going to use what's left here. I don't need to do the original one. Because if it's a 0 of the original one, it's got to be a 0 of that one as well. So again, negative 2 is from my list. 2 times 2 is negative 4. 5 times negative 2 is 10. Negative 10, sorry. 2 times negative 2 is negative 4. Is it a 0? Yes. Now, it's a 0 of multiplicity. 2 has to have even multiplicity. Why? Because the graph just touched. It didn't cross there. So watch what I can do again. Why can I take it out again? It's multiplicity 2. Drop it down. 2 times negative 2 is negative 4. 1 times negative 2 is negative 2. What's the third 0 here? I'm thinking it's negative 1/2. And if I tried that in my half box, what would happen? Is it a 0? Yes. Negative 1/2. You could have also have verified that on your calculator. Yeah. Okay. Hold on just a second. Do you see that negative 1/2 is also in my list of rational? All right. Why did I use the negative 2 here twice? Because it had even multiplicity. Remember what the multiplicity means? When I'm writing that polynomial as a list of linear factors, so x minus 3 times x plus, times x plus 2 squared times x plus 1/2. That's the polynomial written as a product of linear factors. How did I know that that 2 was here? Because I looked at the graph and I saw that it just touched at that x-intercept. It didn't cross. There's a lot going on here, guys. A whole lot going on. And it's nice to just be able to plug that polynomial function into your calculator and look at the pretty little graph that it spits out. But when you're trying to break it all down by hand, it gets very complicated very quickly. One more time, what all did we just do? Let's summarize it. We were given that polynomial. Yep. Yep. Okay, once they gave you the polynomial, you will go to your calculator. You're going to hit y equals and type it in. Now, know that the x that you're using is right here, the xt theta n. And then to get to a power, you're going to raise the little caret symbol that's above the division sign. That means raise it to the power of. Now, once you hit like 2x to the power of 4, you need to arrow to the right to come back down. Once you enter your polynomial in, you go hit graph. And it shows you a beautiful little graph. If the window is off, you can always do zoom and 6. And it puts you back to a negative 10 to 10 on both axes. Okay, they gave you the polynomial. I'm telling you to go look at your graph on your calculator. I'm going to guess that negative 2 is an x-intercept. How could I check that on my calculator? I hit trace, negative 2, enter. Does it tell me the y value is 0? Yes. What's another one that I'm going to guess? Maybe 3. Trace 3, enter. Yes, that's a 0. What was our third one? Negative 1/2. So I could hit trace, negative 1/2, enter. Yep. Now the question was, why is negative 2 done twice? When you look at this graph, we've already discussed multiplicities. An odd multiplicity means that the graph crosses the x-axis at that 0, whereas an even multiplicity means that it just touches the graph at that x-intercept. And on our graph right here, it just touches. Bless you. So I knew that I could take out that 0 at least twice. So I now I did a list of possible rational zeros, and I found 3 x-intercepts that are all from that list. Now I'm going to go do the work by hand. Instead of having to divide all those 16 numbers out to see which ones worked, I cheated. I looked at my calculator and I found 3 of them that worked. And I actually really cheated because I saw the graph of it and I saw that negative 2 came out twice. So by hand, I showed that 3 was a 0. I showed that negative 2 was a 0 twice. And I showed that negative 1/2 was a 0. So now to answer this question, what are the zeros and their multiplicities? There was a 0 of 3. What's its multiplicity? How many times could I take it out? Just 1. There was a 0 of negative 1/2. How many times could I take it out? Just 1. And there was a 0 of negative 2. Its multiplicity is 2. Because the graph touched at the x-intercept negative 2, 0. Let's go do this all again. Find the zeros. X to the 4th minus x squared minus 20. Very first thing I'm going to suggest that you do is go look at the graph. After you look at the graph, I'm going to tell you, what is P? Negative 20. And Q is 1. If that graph has rational x-intercepts, they have to be either plus or minus 1, 2, 4, 5, 10, or 20. Why? Because P is 20, Q is 1. Go look at the graph. Okay, I entered the polynomial into my y equals. I hit graph. What happens? There's 2 x-intercepts. Are they, quote, nice numbers? No, they're 2 and some change, right? So are those intercepts, hold on. When I graph it, it looks something like this. Are those x-intercepts going to be rational or irrational numbers? They're going to be irrational numbers. Well, how in the world do we find them? Do you recognize that that polynomial is quadratic in form? It factors. So I'm going to do this because I'm going to scoot that down. And I'm going to tell you that this polynomial x to the fourth minus x squared minus 20 factors to what? 4 and 5. And then both of those will factor. Do you agree? To x plus 2i, x minus 2i, x plus root 5, and x minus root 5. Hold on, I'll show you. I just know those things. That's a really rotten answer. I'm trying to solve this equal to 0, right? If I had set this equal to 0, so come over and set x squared plus 4 equal to 0. I get x squared equals negative 4, correct? So isn't that x equal plus or minus root negative 4? You have to pull out an I to get rid of that negative under the radical. So I get plus or minus root 4I, which is plus or minus 2I. That's where I got negative 2i and positive 2i as my zeros. I also knew how to factor a sum of squares, which y'all were always taught doesn't factor, right? It does, but it factors over the complex number system. Okay, the other one, this one, x squared minus 5, when I set it equal to 0, x squared minus 5 equals 0. That's a difference of 2 squares. Do you agree? Well, here, I get x squared equals 5, so x equals plus or minus root 5. So that's where I got negative root 5 and positive root 5. All of that is supposed to show you insert humor. Hashtag truth. Hashtag failure is inevitable. Those two x-intercepts are going to be positive root 5 and negative root 5. If I were to tell you, say on a test, to find the zeros of that polynomial, if you know root 5, a bunch of them are going to be on the test, if you know that root 5 is a 0. So I'm going to amend this. Find the zeros if x equal root 5 is a 0. I amended the problem. So now what would you go put in your little half box? Root 5, right? What are your coefficients? 1. Careful. You got to have a placeholder because there's no x cubed. Close, but really far away. Negative 1 for the x squared. What about for the x? 0. And then negative 20. What do you get? 1 times root 5. 0 plus root 5. Now what is root 5 times root 5? 5. Negative 1 plus 5 is 4. 4 times root 5? 4 root 5. 0 plus 4 root 5. Okay, now you've got to do 4 root 5 times root 5. 4 times 5 is 20. Negative 20 plus 20 is... Okay, root 5 was a 0. Because I saw symmetry on that graph, what's another number that I can try over here? Negative root 5. Go do it. Okay, here we go. Bring down the 1. 1 times root 5 is negative root 5. I get 0. 0 times negative root 5 is 0. 4 times negative root 5 is negative 4 root 5. Okay, if I were to write the polynomial is a product of linear factors, what do I have so far? I have x minus that 0. I have x minus that 0, so x minus a negative root 5. And then what's left down here? X squared plus 4. So if I set those equal to 0, what do I get for my zeros? Root 5. Negative root 5, x squared equals negative 4, x is going to be plus or minus root negative 4, which is plus or minus 2i. How many zeros did I find? 4. I found root 5, negative root 5, 2i, and negative 2i. 2 of them are real. They're irrational real zeros. And 2 of them are complex. Question.
Could you explain how 4 root 5 times root 5 is 20?
Yep. Question was, how is 4 root 5 times root 5? Do you see that that's 4 times root 25? Root 5 times root 5 is root 25. What is root 25? What is 4 times 5? Or do it on your calculator.
How do you do it on a calculator?
On a calculator, I'm going to go to my home screen and do 4 square root 5, arrow over, times square root 5, and get 20. Okay, so to answer this question, find the zeros. What are the zeros? The answer should be root 5, negative root 5, 2i, and negative 2i. One more time, these are irrational real zeros. These are imaginary zeros. It was a degree 4 polynomial. How many zeros did I have total? Degree 4 polynomial, there are 4 zeros.